I'm going to talk about fractional Hall effect, and the title is What's New? Of course, there's lots new. You heard this excellent talk by Jim Eisenstein, where he told us about many new experimental results. There will be many other talks in this conference where a lot of new stuff will be presented. I will confine to the developments in which I have participated. And there are three topics that I would like to cover. I have benefited greatly from collaborations with a number of people all around the world. And these are Alex Archer, Kwan Park, Sutirtha Mukherjee, Sudhanshu Mandal, and Arek Weiss, who is sitting right here. In particular, I will try to show that our understanding of the fractional Hall effect is so precise that we can go back to some old, long-standing problems and try to resolve them. So I realized that the audience here is diverse, and therefore I would like to spend maybe 10 to 15 minutes in just giving a broad introduction to the field. It, of course, all started with the seminal discovery of quantum Hall effect by Klaus von Klitzing, which was followed by the discovery of a plateau at 1/3. So that was the first fraction to be observed. In the subsequent years, the number of fractions mushroomed, and the phenomenon started looking like this, which makes it clear that this is one of the most amazing collective states observed in nature. There is evidence for more than 75 fractions now. This, I believe, is the most beautiful single trace taken in physics. It's, you can see the richness of the phenomenon here, and we'll see that it has also given us a huge number of new concepts and structures. Okay, so theoretically, the problem at the most fundamental level is a problem in quantum mechanics. We would like to solve the Schrodinger's equation for a Hamiltonian that has this simple form. This is the Hamiltonian of interacting electrons in the lowest Landau level. So we have to confine ourselves to the lowest Landau level. And we would like to solve this as a function of the filling factor of the lowest Landau level. Now, this actually is an extremely complicated problem because there is no small parameter in this problem. We often like to treat interaction as a perturbation to something, but there's nothing else. Interaction energy is the only energy scale. In fact, there's no parameter at all once I choose the units properly. So we cannot do any perturbation theory. Standard techniques are not applicable. The physics of fractional Hall effect is non-perturbative. It's an inherently many-body state. And just during the ride here, Professor von Klitzing and Jim Eisenstein, we were discussing that fractional Hall effect is actually the most strongly correlated state in the world, because we often define the strength of correlations as the ratio of the interaction energy to the kinetic energy, and here there is no kinetic energy. So the question is, what's the mechanism of fractional Hall effect? So we would like an answer like, for example, in superconductivity, we can say, well, there are Cooper pairs and they're Bose condensed. So what are the analogs of Cooper pairs here, and how do they produce fractional Hall effect? Well, progress in this direction is made by the composite fermion theory. And the basic, I mean, I will not have time to tell you about all the motivation that led to composite fermions, but at least the final statement of the theory is sufficiently sharply defined that I can put it on a single transparency. The physics is that electrons capture an even number of vortices to turn into composite fermions. And one often thinks of a composite fermion as the bound state of an electron and an even number of flux quanta, where a quantum of flux is defined here. And this is how a composite fermion can be shown pictorially. This is a composite fermion carrying 2 flux quanta or vortices. I will use these two interchangeably. In this talk, this is a composite fermion carrying 4 flux quanta. Now, composite fermions do not see the flux that they have assimilated unto themselves. They see an effective magnetic field given by this equation here, which is called B star. It's equal to the external field minus the flux captured by composite fermions. They then form lambda-like levels, which I will call lambda levels, in this effective magnetic field, and their filling factor nu star is related to the electron filling factor nu by this equation. In fact, one can go further and write explicit trial wave functions based on this physics. Here, we first go to the effective filling factor and write the wave function for non-interacting fermions at the effective filling factor, which we know in many cases, especially when nu star is an integer. We know this wave function precisely. And then we use this equation to map this wave function into a wave function of correlated electrons at filling factor nu. So one can show that these equations can be derived from the top equation. So everything in composite fermion theory actually flows from a single equation. Again, just to make the basic point, interacting electrons at magnetic field B transform into weakly interacting composite fermions at an effective magnetic field B star. Okay, so let me make a couple of remarks. So there is a lot of excitement in condensed matter physics about the emergence of exotic particles. So these are emergent particles because they were not there in the original Hamiltonian. They're particles that appear in the solution of the problem. Composite fermions are also emergent particles. They are collective entities because they are bound states of electrons and vortices, and each vortex actually is a collective bound state of all particles. So each composite fermion is an extremely complicated object, and it's actually surprising that one can think of it as a particle. It's also a topological object because a vortex, by definition, is a topological object. We can count the number of vortices. In fact, the fractional Hall effect is doubly topological because the particles are topological, and then they fill lambda levels, which is also a topological effect. So in some sense, we have 2 topological quantum numbers, the number of flux quanta bound to composite fermions and the number of their filled lambda levels. Now, experiments have shown that composite fermions exist. Now, just like in mathematics, existence proofs are very powerful in physics as well, because once you know something exists, you can think about it, you can play with it, you can ask what it does. And of course, you hope it does something, because if something exists and doesn't do anything, it's not much interesting. It turns out composite fermions do lots of things. They, in fact, do a lot of the things that electrons do. And here I have listed some of the properties of composite fermions that have been measured. They have a mass, they have a magnetic moment, they have an effective magnetic field, integer quantum Hall effect, they form a Fermi sea, and we heard earlier, they even form a paired state. What I would like to concentrate on during this talk are fractional Hall effect of composite fermions, their spin polarization, and I would like to try to convince you that they even form a crystal state. Okay, so I like this slide very much. It was given to me by Lauren Pfeiffer, and it was probably made by Pan and Stormer and Sui. So this tells us how we can understand fractional Hall effect in a very simple way. So if you focus on the lower panel, these are integer Hall states, And around filling factor 1/2, we have many fractions that have the form p over 2p plus 1. Then further down in the magnetic field, around filling factor 1/4, we have fractions that have the form p over 4p plus minus 1. Now I'm going to do something very simple, which is to take the upper panel and plot it as a function of the effective magnetic field as experienced by composite fermions carrying 2 flux quanta. Once I do that, you will notice immediately that there is a remarkable correspondence between the two panels. The 1/3 here maps into 1, 2/5 into 2, 3/7 into 3, and so on. So you might as well erase the fractions here and think of these as integers of composite fermions. I hope these integers are visible. The more complicated fractions also match up very nicely with the simpler fractions in the lower panel, and these can be thought of as simpler fractional Hall effect of composite fermions carrying 2 flux quanta, but they can also be understood as integer quantum Hall effect of composite fermions carrying 4 flux quanta by shifting this panel further to the left to correspond to an effective magnetic field as seen by composite fermions carrying 4 flux quanta. So we have a simple physical understanding of a fractional Hall effect. We understand why fractions appear in the form of these sequences. And in fact, we understand why there are sequences at all, because it all derives from the sequence of integers. All the fractions are explained in a unified manner. In fact, the fractional Hall effect and the integer quantum Hall effect, they are also unified. This comparison actually is a confirmation of the effective magnetic field. And I should say that this physics has been confirmed through numerous experiments that I will not have time to go into. What I would like to tell you, and that will be important for the rest of the talk, is I would like to give you an idea of the accuracy of the composite fermion theory. So for this purpose, I would do 2 independent calculations and put the results on a single plot. One calculation would be to produce exact spectra of some finite number of electrons by putting them on the computer and doing a brute force diagonalization. The geometry we will use is called the spherical geometry. The electrons move on the surface of a sphere exposed to a radial magnetic field, which corresponds to 2q flux quanta. So this defines 2q. So the only 2 numbers I need to know are n and 2q to produce all of these exact spectra. The appropriate quantum number for this geometry is the total orbital angular momentum, and the states will be labeled by this orbital angular momentum called L. Okay. Now, the second calculation I'm going to do is take these wave functions, trial wave functions I showed you earlier, and evaluate their Coulomb expectation value. Now, for the ground state at 1/3, we already have a beautiful wave function by Laughlin. And the reason why we believe in Laughlin's wave function is because when you evaluate its energy, you get these dots. And you can see that there's a beautiful agreement between the energy of the state and the exact energy. I should also tell you that there is a number at the top here, and this tells you how many states there are in a given angular momentum sector. And I believe there are several hundred states here, so a comparison here is very non-trivial. Now, we would like to think of these states as 1 filled lambda level of composite fermions, 2 filled lambda levels here, and 3 filled lambda levels here. It turns out that 1 filled lambda level gives me the same wave function as the Laughlin's wave function, and therefore I do expect the same results, so it's not surprising. The true test of composite fermion theory would be if these wave functions work. So there are precise unique wave functions associated with these pictures here, and we calculate the expectation values of those wave functions, and we get the dots here. So this was the time when we knew that this is also a quantitatively very accurate theory. Well, one can go further and ask whether this branch of excitations can be understood as a particle-hole pair or an exciton of composite fermions. It turns out that these also have unique wave functions associated with them once you fix the total angular momentum. So we go ahead and calculate their energies, and we get the dots here with no adjustable parameters. So there's no fudge in either of the calculations. You know, we cannot change the result at all. We get what we get. Well, this was already 10 years ago. Now it's possible to do much larger systems, and these are from 14 to 18 particles, from 1/3 to 3/7, and you will notice that the number of states in each angular momentum sector goes from 100,000 to several million. So these spectra show you this extreme low energy part of the full spectrum. Again, we can take the unique wave functions of composite fermions, and we get these dots here. For later in this talk, I will also need to use the fact that we can also construct wave functions of composite fermions at filling factors other than these special filling factors like 1/3, 2/5, and 3/7. So at an arbitrary filling factor, when you go to composite fermions, you get a partially filled lambda level. We don't have a unique wave function anymore, but we just take all of the possible wave functions. The number of these is much, much smaller than the number of wave functions we had for electrons. We then composite fermionize these wave functions, and please take my word that we can do diagonalization of the full Coulomb interaction in this basis to produce the spectrum for composite fermions. Okay, so here are 3 results. These are systems from 12 to 16 particles, somewhere between 1/3 and 2/5. And when we do our composite fermion diagonalization, we get these dots here. So in all of the cases we have tested, we find that the composite fermion theory is accurate at the level of 0.05% for the lowest lambda level physics. It can be basically treated as exact. It's probably clear to you that it's not a theory of one wave function. It gives you a quantitative theory for all states in the lowest lambda level. It tells you what the incompressible ground states are, what their neutral and charged excitations are. It tells you what the low energy spectrum is at an arbitrary filling factor. It gives you partially spin polarized or spin singlet states and their excitations. It tells you compressible states, and so on and so forth. Just for fun, I would like to mention that the most stringent exact diagonalization that I showed earlier, which was carried out by Professor Voice, it would require about 11 years of time on a single compute core. The composite fermion diagonalization will take about 1 week. So we have to do some Monte Carlo to evaluate some matrix elements. Even more impressively, with composite fermions, we can go to much larger systems. For example, we have studied systems with up to 200 particles. And I'm going to show you results for a system where the L = 0 sector contains 700 trillion states, which could never be studied by exact diagonalization. Okay, so now I come to the new part. This was all introduction. The first thing I would like to talk about is the crystal phase. Some of you may know that Tsui, Stormer, and Gossard, they discovered the fractional Hall effect when they were looking for the Wigner crystal. And the idea was very simple. If you force all electrons into the lowest lambda level by application of a very strong magnetic field, then the kinetic energy is suppressed. So what could electrons do but form a crystal? It turns out they form composite fermions, but we still believe that if we go to sufficiently small fillings, eventually a crystal phase would be produced. One can actually do a variational calculation where if you look at the lower plot, these are the energies at the special filling factors for the liquid state, and the dashed line is the energy of a wave function for the crystal written by Lamb and Gerwin in 1984, and there is a crossover at a filling which is roughly 1/6. Indeed, experimentally, it's seen that there is fractional Hall effect at 1/5, but when you go to filling factors below that, the system is insulating, which is consistent with the presence of a Wigner crystal, which is localized or which is pinned by impurities. But there is another very interesting thing seen experimentally, which is that even between filling factors 1/5 and 2/9, there is a very large resistance peak, and this peak has not gone away as the sample quality has improved by an order of magnitude or even more. So it's believed that this is an intrinsic effect, and there is no explanation for that. This is what we would like to understand. It turns out that the explanation of this requires an extremely accurate understanding of the crystal. In fact, it tells us something about the crystal. It sheds some light on the nature of the crystal. And it also requires us to complete this curve for the fractional Hall energies. So we want to be able to connect these dots. So we proceed as follows. First, let me tell you what the most accurate crystal is. So here is the Marquis-Zotos crystal. That's the simplest one. We put electrons in localized Gaussian wave packets in the lowest lambda level and put them in a triangular lattice and antisymmetrize the whole wave function. One can ask how well does this compare with exact diagonalization results. Here, the exact diagonalization is done on a disk for 6 particles at the filling factors shown here. At 1/3, the Laughlin wave function has fairly large overlap with the exact state. But as you go to smaller fillings, the overlap goes down. On the other hand, if you look at Marquis-Zotos crystal, and I should note parenthetically that here we have projected this crystal into a definite angular momentum state before comparing with the exact state. So it's like a rotating crystal. You will notice that its overlap increases as we go to smaller fillings. Nonetheless, the overlap is not very large here. So a question can be asked, is there some other crystal that we can construct that would give us a better description than the Marquis-Zotos crystal? Well, it's natural to think of a crystal of composite fermions. So we take the Marquis-Zotos crystal and multiply by this Jastrow factor, which attaches 2p flux quanta to each electron. The value of 2p is determined variationally by asking what value gives the lowest energy. It turns out that the composite fermion crystal just has a marvelously good agreement with the exact state. So its overlap with the exact state is actually larger than the overlap of Laughlin's wave function for the 1/3 state. And that's all the more impressive when you notice that here the size of the Hilbert space is approximately 500,000 as opposed to the size at 1/3, which was only approximately 1,000. The energies are almost exact. In fact, this gives us an almost exact understanding of the crystal state. Okay, so how do we model fractional Hall states in between the special fractions? Well, in between the special fractions, we have a partially filled lambda level. So what we are going to do is place composite fermions in that partially filled lambda level in a triangular crystal arrangement. This crystal would be referred to as a type 2 composite fermion crystal. The language is reminiscent of type 2 superconductors, because there you can have a crystal you can have an abrikosov lattice which lives on top of a superconductor. Here, the type 2 composite fermion crystal lives on the top of a fractional Hall state. So this state has zero resistance and a quantized Hall resistance. These are pictorial representations. So this is Marquis-Zotto's crystal. This is a composite fermion crystal at a filling slightly above 1/5. And you will notice that these two look very similar, but here the wave function is a little more delocalized near each lattice site. This is a crystal of composite fermions on top of 1/5 state. A composite fermion at the second lambda level has this ring shaped. It's like a smoke ring. And you will see that we get a crystal of rings here. As you start increasing the number of composite fermions here, eventually the rings start interfering to produce this rather complicated patterns as shown here. Okay, so now we have both of the ingredients, and with a lot of hard work by my student, we can now ask what do we get. So this is what we had earlier. The picture that we get now is given here, and it shows that the phenomenon is much richer and much more colorful, actually. So these are the energies of the fractional Hall states, and they show these cusps. These cusps, I believe, have been calculated for the first time. And you will notice that this crystal phase, it actually goes below the fractional Hall phase in a region between 1/5 and 2/9. So this is where we have a crystal of composite fermions carrying two vortices. Marquis-Zotto's crystal would never cross this line, and even Lamb-Gerwin crystal would not cross this line. So you need to have an extremely accurate theory to see this reentrant behavior. Now, the other interesting thing we find is that as we go to smaller fillings, we do not have a monolithic phase. We actually have a phase which is rich with structure. We have crystals of composite fermions carrying 4, 6, 8, and so on vortices. So one can ask, how would we see this phase diagram? Well, this is still work in progress. But one possible way is to notice that the shear modulus of the composite fermion crystal has discontinuities. So it goes from here to here, and suddenly it has discontinuities at the phase boundaries. And at least in an ideal situation, these discontinuities will translate into discontinuities in the pinning frequency, melting temperature, or other properties of the crystal that may help identify these phase boundaries. How much more time do I have?
10 minutes.
Okay, that's good. This is the second topic. And here I'm going to talk about composite fermions with two components. These two components could be either spin or valley. And in fact, for systems like graphene, one can have 4 components, but I won't have time to talk about that. And I will use the language of spin, but with the caveat that it applies to also valid degree of freedom. We had generalized composite fermion theory to include spin many years ago, and the generalization is straightforward. Let's consider filling factor 4/9, which maps into 4 filled lambda levels of composite fermions. Now, all we have to say is that some of these are occupying spin up lambda levels, and some are occupying spin down lambda levels. So if we have 2 spin up lambda levels and 2 spin down lambda levels, then we get an unpolarized state. When we have 3 and 1, that's a partially polarized state. And when we go to 4, 0, that's a fully polarized state. So this immediately tells you what are the possible spin polarizations. And furthermore, we can actually calculate the energies of these various states, get their thermodynamic limits very carefully, and predict and make a prediction for the Zeeman energy where we expect the transitions to take place. So these are old results. Transitions were studied by Du et al. many years ago, and by Kukushkin et al. And Professor Klitzing's group, by transport. Sorry, this was by transport. This was optical experiments. And more recently, in Bansur Shagan's group, this phenomenon has been studied in aluminum arsenide quantum wells, where valleys play the role of spin. And these two panels show comparison between theory and experiment. So these, OK, you can see which are theory and which are experiment. So given the fact that the Zeeman energy depends very sensitively on this very small energy differences, we find that the comparisons are rather satisfactory. Also, they don't include finite thickness effects, and there is also disorder, which also may complicate things a little bit. Now, we have extended this comparison to arbitrary filling factors recently. When we go to arbitrary filling factor, we have partially filled lambda levels of composite fermions, and the question is, what state would these composite fermions would make? Well, we make the approximation that they form a crystal. And one can show that that's a reasonably good first approximation. With that approximation, we can go ahead and calculate the phase diagram as a function of the filling factor. If you look at the blue lines here, these are the results of our calculations. The triangles were known before, and earlier you might have been tempted to connect these triangles, but it turns out that the phase boundaries go sideways, and they go across several lambda levels, several plateaus. One can also use an effective theory, which is a theory of free fermions, with one adjustable parameter, which is the effective mass of composite fermions. And by the green lines show what we get using that simple theory, where we have chosen the effective mass of composite fermions to get coincidence at this point. Well, fortunately, these phase boundaries as a function of the filling factor have been measured recently by Amir Yacobi's group at Harvard. And these are the compressibility measurements. This is at filling factors P over 2P plus 1. The x-axis actually is the filling of composite fermions. The y-axis is the Zeeman energy divided by the Coulomb energy, where one has made the approximation that the Zeeman energy is that the G factor is 2, and the dielectric function is 3. Okay, that's kind of an arbitrary. These quantities are not precisely known at this moment. So at any filling factor, you notice that as a function of the Zeeman energy, there is a transition at certain points. And these are the red lines are results from our microscopic calculations. The green lines are results from the free composite fermion model. And you can judge for yourself how good or bad the agreement is. Here is a similar comparison at filling factors P divided by 2P minus 1. These are states where the flux points in the reverse direction. And again, you see it seems a fairly good agreement. In fact, there was also a paper recently by Koji Murake's group, where they measured the spin polarization as a function of the filling factor. This paper actually concentrated on the spin polarization at 5/2, but it also had results in the region that we are interested in. And the blue dots are their results. The red lines are what we would get from the phase diagram that I showed earlier. So there's a reasonably good agreement between theory and experiment. But to make things more precise, of course, more work would be needed. OK, now I shift to my third topic. And I earlier told you that the fractional Hall effect is the integer quantum Hall effect of composite fermions. It turns out not quite. It explains most of the fractions, but it does not explain all the fractions. In fact, there are fractions which cannot be understood that way, which indicates that there is physics where we where we must either treat interactions between composite fermions or go to an altogether different theory. There is such physics occurring in the second lambda level, in particular the 5-half state, cannot be understood as in terms of non-interacting composite fermions. It's a state where composite fermions pair up. I'm not going to talk about that. I'm going to focus on the structure that's seen here. 1/3, as you may remember, is one filled lambda level. 2/5 is two filled lambda levels. So this is a state of composite fermions where they are filling the second lambda level. Okay, one can assign filling fractions to these states. These are 4/11s, 5/13s, and 3/8s. Tilted field experiments that ask how the structures change as a function as we vary the Zeeman energy show that these states are not very sensitive to changes in Zeeman energy, and that suggests that these are fully spin polarized states. Well, we know that whatever these states are, they are some states of composite fermions. A priori, we could have thought of either crystals or stripes or fractional Hall states, but experiments clearly point to a fractional quantum Hall effect at these fractions. When we go to composite fermions, 4/11s maps into filling factor 1/3 of composite fermions in the second lambda level, and 5/13s maps into filling factor 2/3 of composite fermions in the second lambda level. So it seems rather natural to say that these are Laughlin-like 1/3 and 2/3 states of composite fermions in the second lambda level. But we are going to question that assumption here. And the only reason we are going to do that is because of this very nice paper by Weiss, Yi, and Quinn many years ago. They do the following in this paper. They say, let's model composite fermions at the second lambda level as fermions interacting with a two-body interaction. Let's evaluate that interaction by placing only two composite fermions at the second lambda level, and that gives the pseudo-potentials for the interactions. Pseudo-potentials are energies in different relative angular momentum states. And then we are going to forget about electrons. We are going to just consider a problem of fermions interacting with this interaction. What they concluded was that 1/3 fractional quantum Hall effect does occur, but at a flux value given by 3n-7. Now, to most of you, this doesn't mean anything. But to the practitioners, this 7 is somewhat shocking, because this says that this state is topologically distinct from Laughlin state, which occurs at a different flux value. Okay, so I remember that John, when he told me about this many years ago, I did not take that seriously because it was too bold a claim. Also, there are a couple of things that could go wrong with this calculation. One is that the interaction between composite fermions is very complex, and one could wonder whether a two-body model captures the physics properly. And also, the ground state from this calculation cannot be compared directly to the exact electron ground state at filling factors 4/11s and 5/13s. So anyway, recently we went back to this problem and put this into our composite fermion diagonalization routine. And here are the results directly at filling factors 4/11s and 5/13s at the flux that corresponds to the theory of Weiss, Ye, and Quinn. And the results go up to fairly high numbers of particles. The thing that you would notice in this, or the main thing I would like you to notice, is that for all of these panels, the ground state is a uniform state at angular momentum 0. So that, it's for all of these cases, the ground state is an incompressible state, and that strongly supports the mechanism proposed by Weiss and Quinn. Well, we can go further and construct explicit wave functions for these states. We do it as follows. We take this interaction, calculate its ground state. It turns out that it's not a simple state, but we know it numerically. We put that in the second lambda level, and then we composite fermionize the whole thing to get an explicit wave function at filling factor 4/11, and then we compare it to the wave function that we get from composite fermion diagonalization. And these are the overlaps between those two. And the overlaps are extremely large. They're surprisingly large, which, in our opinion, fully confirms the Voisin-Quinn mechanism for the physics of filling factors 4/11 and 5/13. These are unconventional fractional Hall states. They represent a new class of fractional Hall states. And they occur because of this rather peculiar interaction between composite fermions in the second lambda level, which maximally penalizes composite fermion pairs with angular momentum 3 rather than 1. Okay, you could ask, well, how do we test this? One prediction that we can make directly is perhaps testable. We had studied a partially spin polarized state where we put 1/3 of the composite fermions in the spin reversed lambda level many years ago. And by comparing these two energies, we predict that the transition from the partially polarized state to fully polarized state should occur at a value of Zeeman energy divided by Coulomb energy given by this formula here. So that corresponds to a magnetic field of 19 Tesla for gallium arsenide, which immediately leads to two predictions. One, the state observed by Pan et al., which occurred at 11 Tesla, is partially spin polarized. The only reason why it was not sensitive to changes in the Zeeman energy was because its excitations did not involve spin reversal. Prediction number 2 is that a transition to a fully polarized state should occur when the Zeeman energy hits this value. Okay, so I think I'm running out of time, so I'm going to skip the final part and just go to the conclusion slide. The main conclusion is that we now have a sufficiently accurate understanding of fractional quantum Hall effect in the lowest lambda level, and we can address very subtle issues now. Let me also say that the part that I skipped, which related to filling factor 3/8, at this filling factor, we believe that fractional Hall effect appears possible, and if it occurs, it's very likely an anti-Pfaffian paired state of composite fermions, and that would be very interesting because that would provide another example away from 5/2 for pairing of composite fermions. Thank you.
Thank you very much for very interesting talk. So the paper is open for questions, comments. Any questions? Oh, yes.
When I look at the comparison of your spectra, composite fermion and exact diagonalization, there seems to be a shift between the two spectra. Where does this come from? So your dots do not fall exactly on the lines.
Well, the composite fermion theory is not exact. It's surprising that the results are so close. It would be too much to ask for the results to be exact. But they are within 0.05% of the exact energies. So I think the question to ask would be whether this difference is small compared to the gap separating these states and the other higher energy states. Okay, and that always is true.
I would just like to make a comment that Duncan Haldane introduced a composite fermion hierarchy, which assumed that the quasi-particles in a Laughlin correlated electron state were themselves Laughlin correlated, and he assumed that happened everywhere. And he found all odd denominator fractions. Now, Jainandra came along and said, well, the most robust states are the ones that correspond to integer filling, because then you don't need any interactions between the composite fermions. And he said the interactions are not so important. But in the case that he's talking about 411s, Piotr Sitko, who worked with me and Kyung-Soo Yi at Brown in the mid to late 1995, 96, someplace in that area, we showed by simple numerical calculations that Haldane's picture was not true for a 1/3 filling of composite fermions. And we said that we thought that it failed because the interaction was not sufficiently similar to the Coulomb interaction. And I do believe that's true. And I think that's what Eric and I we were able to explain in our own way, which Jainandra didn't believe for a long time. But now I'd say we're both in agreement. We're both in agreement as to what the 411 state is. Thank you.
Okay, just an addendum to that comment. Duncan Haldane did not introduce composite fermion hierarchy. He did not know composite fermions. So I think that's, I would like to make the comment that Laughlin quasiparticles and composite fermions, they're distinct objects. Laughlin quasiparticles do not have integer quantum Hall effect of Fermi C and so on. So there has been some confusion in the community where people tend to equate these two things.
Could you explain why you were using this geometry for Wigner crystal?
Well, so I did not have time to point this out, but you cannot wrap a Wigner crystal on a sphere without creating some defects. So that was the reason we were using this geometry. Now later on, the results, these beautiful pictures I showed you, were for composite for crystal on a sphere. And there we used this old model by J.J. Thomson, which was the plum pudding model for the atoms, where we put the composite fermions at the positions that minimize the energy of a classical system of charged particles. Okay, so that actually gives a crystal that's locally triangular and has very few defects.
It's a triangular lattice that cannot be wrapped on a Haldane sphere.
That's right, triangular lattice, that's correct.
Any other question? Oh, yes.
So in your first part of the talk, you have predicted several kinds of Wigner crystals. So as their boundary, do you expect a first-order transition or second-order transition between these crystal faces?
Well, in the absence of disorder, where did the question come from? Can you? Oh, okay. Okay. In the absence of disorder, we believe it has to be a first-order transition because the vorticity bound to composite fermions cannot change continuously. Of course, with disorder, it would become a percolation transition, which would be a continuous transition.
Any other questions? Okay, so if not the case, let us thank the speaker again.